Hi, welcome to Functional Justin episode 15. My name is Justin Hayes Jones. I've been making a series of videos about functional programming, and this video is going to require some knowledge of Scala and functional programming and some of the Haskell-y type classes in general. What I'm going to do is answer the question you quite often see on Twitter: is it always traverse? And what that means is there's a type class called traverse, and it's extremely versatile, so you can solve lots of different problems with it. So what we're going to do is just take the very first day of Advent of code, and if you don't know what that is, you can check the link under the video, and we're going to try and solve that problem using the traverse type class. Now, two caveats to this video. First one is this is not a good way of solving problems. Don't pick a type class and then go and look at the problem. That's exactly backwards. You should really solve the problems with the most appropriate tools for the job. And the other thing I'd like to point out is I'm not solving this problem in real time. I already sort of figured out the solution, so I'm just gonna retrace my steps. I'm definitely not smart enough to make a video where I solve this in real time. So let's go into IntelliJ and take a look at the code. So our starting point is we have the I have a project set up. I'm using Scalaz version 7.3 for the type class library, for the traverse type class and the Monoid implementation and whatnot. If you're not familiar with Scalaz, it's a very mature library that provides category theory and Haskell style type classes, and that's what we'll be using. So the starting point is we've got the example input from the problem. And if you're not familiar with Advent of code, the way it works is the answer is usually something that you can just paste. Well, it's always something you can just paste into a box and see if it's the right answer. So in this case, the answer is going to be a number. And what they give you is a sample input that you can use to test your logic. And then they give you a usually much larger input that you can use that is your personalized input to see if you've solved the problem or not. So I've already gone ahead and loaded those. So I'm going to load the input from a resource file. So that's the bigger input, and then the example input is just this smaller list of numbers. And the problem we want to solve is to go through this list, and we want to take note of all of the values that are bigger than the one before them. So in this case, 200 is bigger than 199, so that would count. This one's bigger, so that would count. This one's bigger, that would count. This one's smaller, so it wouldn't count, and so on. And the correct answer here should be 7. There's actually 7 numbers there, and we know that because they give it us in the on the page, and we also can easily figure it out ourselves. So the question is, how do we solve this with traverse? So the obvious solution to this would be some kind of for loop. So just to go through each element and keep track of the previous element, and then you can do the comparison, and then you can increment a mutable counter. So obviously we can't do any of that if we're doing this in a pure functional way. Instead, what we're going to do is use traverse. So I'm just going to begin by showing you what you can do with traverse so that we can start to think about what the solution would be. So first of all, let's just map our list in different ways so that I can just introduce traverse if you're not familiar with it, and show the kind of things we can do with it. So we summon an instance of the type class for list, traverse list, and then we're going to call the traverse function on it. And the traverse function itself takes an input list, so that's going to be our example input, and then it takes a function. So we're going to take some value, and then we're just going to return the value. Now you can see we've got IntelliJ shows these implicit errors now, so we can see that we don't have evidence for applicative. So if we just take a look at the types here, we can see that traverse, let me just whiz up to the top here, the traverse type class takes a type parameter of f, which must be a functor, and it must be foldable. So functor means it's something that's mappable, and foldable means it's something that, as it says here, it has the ability to extract one or more values of that type. So in our case, what that means is we're going to be able to extract the values of the list and do some processing on them. Now let's look at the traverse function. The traverse function also has a type parameter g, which must be an applicative. I'm going to put some links under the video about what applicative is. I'm not going to go into it in detail in this video because it will be too long. But the idea is that we take our foldable and then we use the applicative to go ahead and applicative has an operation called app, and it takes two parameters. So what we're going to do is use this function to create an instance of our applicative, and then the app operation will apply to each of those elements in turn. And so that sounds super abstract, so let's take a look at a concrete example. Now if we were to say let's take this number from the example input. Remember, n is each of the integers from our input, and we're going to just cast it to be the type ID. So ID is a type, I'm just going to call this out. So ID is a type which has monad instance, and therefore it has an applicative instance. Remember that all monads also are applicatives and functors by definition. So what that does is ID has an applicative instance which just appends values. So what we're doing here is, if I run this, you'll see, is essentially what we've written is just a map function using traverse. And the beauty of traverse is that by combining these two different type parameters, f and g, we can get very different behavior depending on the types that we use. So anyway, ID has an applicative instance which just concatenates. So you can see in the output, all we did was make a copy of this list. So it's just a map function, and what we can also do is we can show that we can modify the value just like you could in a regular functor. So there you can see that all the values are incremented, or we could perhaps change the type. So we just need to change the type parameter on the ID. And there you go. So what we did is we're just using traverse to do mapping. Now if you go back to what our problem is, the problem of looking at consecutive values and determining how many of them are increasing, it's difficult to see how we could do that with just a map function. So there's other things we can do with traverse. One of them I can demonstrate by making a tuple. So let's take a tuple and we'll just we'll make a tuple 2 where both of the values are n. Now you can see I don't have any errors here because tuple 2 does have an applicative instance, and we'll see what that does. So you can see that my output list has two values. It returns a tuple 2, and the first value is this large number, and then the second value is the original list. And that's because the applicative instance for tuple 2 will do an accumulation or a fold on the first value, and it will just return the second elements concatenated. Right, so why it does that is kind of historic reasons you can dig into. But for our purposes, that gives us an advantage to solving this problem, is that we know that we can use folds now. We can basically do a reduction on the input list. So if we can find a way to reduce this list and give us our answer, then we've solved the problem. The next thing we can do is there's a data type called const, which is very similar to tuple 2, except that what const does is it still has that that appending reducing operation on its parameter, but it doesn't have a second parameter. In fact, const has two parameters, and it essentially just drops one of them. So what we need to do is decide our type. So we're going to say it's going to be an int. The second parameter can be anything because we just ignore it. Now I'll have to drop a link to explain const a bit more because, again, I don't have time to go into that. But what we've got now is a function which does a reduction on our list and just returns the sum of the list. And you can see that the output is now of type const, but we don't want const. What we can do is we can do get const, and that returns the contents. So now we have a function which takes our list and reduces it down. So we're still a little way off from an actual solution. But one thing we can do is, well, first I should really acknowledge that this concatenation process works because int has a monoid instance which involves addition. So because there's a lot of magic going on in the background here, this applicative, the behavior of applicative for const is in the background. You have to know about that, and then you have to know that it concatenates using monoids. So you have to know about monoids. But essentially what that means is if we can come up with a monoid representation of our problem and then reduce it by appending everything, then we've solved the problem. So all we need to do to solve this problem is figure out what the monoid instance is that we're going to need to be able to take any two of these elements and compare them and somehow propagate a count for the number of increasing elements in the whole list. And let's take a look at what that's going to look like in terms of actual data structures. So what we're going to start with is, let's say we've just got the numbers 1, 2, 3. Now, if we're to append these things together using a monoid append function, then what we've got to do is look at what information we need to be able to carry forward a sort of count of all the increases. So let's say instead of just having these numbers, and remember that here when we create our monoid instances, this can be any type. So we can obviously make our own sum type. We can make our own product type with different fields that represent the different things that we're interested in. So as well as the actual numbers, how about we also propagate a count of the numbers, and we can start off just giving them all the count of 0. And then you can imagine that when you start to append things together, and importantly, you can append things in any order, so we can't assume what order they're appended in. So we could append the 1 and the 2, and then the result of that we could append to the 3, or we could append the 2 and the 3 and append that to the 1. And we have to have the same result every time for it to be a monoid. Another thing we need to take into account is that an empty list will actually use the concept of a 0 value. So remember, a monoid has a 0 value, which is something that can be appended to the other elements without changing them. So when you traverse a list, it has to be able to account for empty lists, and that means it has to return the 0. So with the 0 value, obviously the count is going to be 0, and that's fine. But we also need to think about what this second value is, because if we make it 0, it's going to interfere with the actual count of the real numbers that we're interested in. So hopefully that what I mean by that will become clear as we go forward. So let's take a look. Let's say that we combine the 0, 1 and the 0, 2. So what we're going to say is if the number increases, then we increase the count. So when we combine these things, the first element of our structure is going to be the count, so that gets incremented to 1. And then the next question is, what value do we use next? If we were traversing left to right, we could always use the 2. So then when we combine this with the 3, things will still work. But remember that we can append in any order, so we might actually append to this one next instead. In that case, if we put a 2 here, that would give us an incorrect value. What we really should be comparing is the 1 and 0. So what that suggested to me is that we need to track not just one value, but we need to track the leftmost value we've seen and the rightmost value we've seen. So let's just sketch out what that data type might look like. So we've got a case class, and we're going to call it, let's call it count increments. Count increment, and it's going to have a field that is going to be our count. Then it's going to be the leftmost value we've seen so far and the rightmost value we've seen so far. And what we could do is create a monoid instance for this type and engineer that monoid instance so that it behaves exactly as we need to solve this problem. So the way this is going to work now is when we compare the 0, 1 and the 0, 2, the first thing we do is increment the count, so now it's 1. The next thing we do is, one thing I need to do is fill out these right values. So remember, we've now got count, left value, and right value. And initially these can all be set to the original value in the list. So our first state is going to look like that. The next thing we're going to do is combine the 1s and the 2s. And so we've incremented our count, and now what we need to say is the leftmost thing we've seen is a 1, so left is 1, and the rightmost thing we've seen is a 2. So now we've combined these two elements. The next thing we're going to do is combine that with the 0 and the 3, 3. And we'll just ignore the 0 value for now. We'll just come back to that one in a moment. So combining these two, once again, what we're going to do here is compare the rightmost value, which is 2, with the leftmost value we've seen, which is 3, and that's an increase. So now we increase the counter. The leftmost value we've seen is still 1, and the rightmost value we've seen is now 3. So now we end up with that. So you can imagine that taking our original list and crushing it down using these appends in any order we want is going to give us the answer we want, is going to give us the right count. So just for our own peace of mind, let's see what would happen if we had a non-incrementing number. So we combine these two. Our count is 2 on this one and 0 on the other one. And this is not an increase. So 3 to 2 is not an increase. So we don't increase the count. Our leftmost value is 1, and our rightmost value is now 2. So you can see that the left and right values essentially sort of extend outwards when we append, so that we're always looking at the correct edge of computation, or the essentially we're propagating forward the numbers that we should be interested in, no matter what order we append everything together. All right, now the tricky part is the 0 value. So if we naively use this, and then let's say our count is 2, and then we've got 1, 2. When we combine them, our count is going to be 2, our leftmost value is now 0, and our rightmost value is now 2. So combining those two gives us the correct value, but remember that the 0 value can be appended on either side. That's one of the rules of being a monoid, is that the 0 value mustn't change. It mustn't be important when it's applied, because it mustn't change the computation. So let's see what happens when the 0, 0 is in the middle of the computation. So let's say we start with 1, 0, 1, and then we've got 0 in the middle, and then we've got 0, 2, 2. Now if we leave the 1s alone, but we squash the 2s together, then first of all, comparing 0 to 2 is an increment, so we increase our count to 1. Then our leftmost value is now 0, and our rightmost value is now 2. So then we come to compare the next element. Just going to wait for the dog to stop barking. So now when we combine these two, the elements are increasing, and so our count goes to 2. Our leftmost value is 1, and our rightmost is 2. So now our count is 2. But if you look at the original list was 1, 0, 2. And remember that our 0 value has to have no impact on the final computation. So you can see that it's messed up by counting itself as a increase when we didn't want it to. And depending on where you put it in the list, it messes up the computation. So the trick is, we want the 0 value to not have any effect on the computation. So the way we do that is, obviously the count has to be 0, because we don't want it to affect the count. The other thing is, we want the left side to be very negative. So in our code, we can use the maximum value for whatever number type you're using. So if this was a really big negative value, then comparing it with values on the left, it will never be bigger than, right? So that's our safety measure there. And then we can use a really big number on this side, and that means that when you're comparing it to things to the right, the thing on the right will never be bigger than it, so it will never increment the count. So those two things together give us what we need to solve the problem. So let's take this and we'll move it up here. And what we need is to create a monoid instance for our new data type. So we're going to make it implicit so it gets picked up by the traversal code, and we can call it whatever we want. So we'll just call it the count increment monoid. The type of that is going to be a monoid count increment. And to define that, we're going to use a helper method in Scalaz to create monoids, and that is called instance. So we can create a monoid instance like that, and monoid instance takes two parameters. One of them is our append function, and the other one would be our zero function. So I'm just going to put that in brackets. So first, our zero function, we'll just define that as count increment. Remember, our count was 0. Our leftmost thing we've seen is going to be the min value, and our rightmost thing we've seen is going to be the max value. And then what we do for the append function is we're going to expect a tuple of the left and right values. So we'll take the left here, and this is of type count increment, and the right is of course count increment as well. And what we have to return is a count increment which combines these two things. And that's not a colon. No, it is. So what we want to do, the new count increment, and we'll figure out what the count will be. Remember that what we want to do is widen out what our leftmost thing and rightmost thing is. So our leftmost thing is going to be the left-hand side's left value, and the rightmost thing is the right-hand side's right value. So that's straightforward. Now the other thing we want to do is increment the new count, or calculate the new count. So the current count on the left is left count. We want to add that to the right count so that our counts propagate through. And the other thing we want to do is potentially add another value, or add one, if this is going from left to right is an increment. So we'll make a variable called inc, and we can set that to if the right value is less than the left value, then that's 1, otherwise it's 0. So if you think about that, we have a thing on the left, and what we're doing is comparing the rightmost thing we've seen so far with the thing on the right's leftmost thing it's seen so far. And if it increases, then we have to increment our counter. So essentially that's the main solution, assuming everything works correctly. What we need to do is, instead of using integer here, we need to use count increment as our type. And we need to create a count increment with each value that we get from the list. So the first, the count is going to be 0, and both the left and the rightmost values we've seen so far are both the current value that we're getting from the list, so that's n, which is an integer. And that should essentially be it. So we run that. There we go. And you can see that what we got out was count increment. We've got the left and right values, and the correct answer is 7. That's what we're looking for. So it seems that everything worked. And then for the real part of the advent of code, we need to use the data from the file that we got. So we can take part 1 input, plug that in there instead, and we'll get a much bigger value, and that's the 1529. Now if you do this yourself, if you run the code yourself, you'll have your own input. This is the correct answer, I just remember from earlier, and so that works. So the answer to the question, is it always traverse? In this one instance, yeah, it seems to be it seems to be traverse. So the next thing we want to look at is part 2. So part 2 is essentially the same problem, but what it wants to do is look at 3 elements, sliding windows of 3 elements. So give me the sum of these 3 numbers, and then move along one and give me the sum of these 3 numbers, move along one and give me those 3, and what that gives you is a new list of the sums of a sliding window going through here with the sums of each of the numbers, and then it wants a count of the things that increased at each stage. So the input is the same. Now what we want to do is we can still use our exact same solution here because the final part is exactly the same, just measuring the differences between 2 things. So what we're going to do is just cheat a little bit and change the input data that's going into our solution. So let's call it part 2 input. And what this is going to be is our original input. So that's part 1 input. And we're going to zip it with the tail of itself. And what that will do is give us a sort of sliding window of 2 elements. And then we're going to zip that with the tail of its tail. And what we get here is, you can see we're getting a list of an int of a tuple of ints. So we'll just make that concrete. And what I'll do first is just print that out so you can see that this represents the sliding window of 3 things that we wanted. Part 2 input. And when we run that, you should see that, oh sorry, I missed a step. So what we've got here is the list of a sliding window of the list of 3 things, and that's not the final thing that we need, but it's a start. So the next thing we want to do is make a new list that's just the sum of those things. So we can take the input and map it. And remember, we're getting this interesting thing of a tuple with another tuple inside it. And we can just return a plus b plus c. So now we have a list of ints. So let's print that. That should be more in line with what we're expecting. So if I was to do that with the sample data, you would see that that matches up with the one in the problem solution. So that so far so good. And the final step is to take our code that does the traverse. So I'm just going to rename these variables and change this to part 2 input. What's the type mismatch here? So, oh, I'm using the wrong data structure. So sums is the input list that we wanted. Run that. There you go, and the answer is 1567, which again is the correct answer. So anyway, that's the end of the video. Hope you enjoyed it, and I'll see you next time. Thanks.